very good evening to all of you. Thanks for coming in over here on this particular Wednesday evening. My name is Mayuresh. I am the co-founder of DataGiri. DataGiri is a community of data science professionals. We started off as being based out of Mumbai, India. So I'll just take maybe 5 to 7 minutes of your time. I'll just quickly introduce to you, who we are, what is DataGiri, and why we are in this part of the world, kind of taking this thing forward. So as I quickly said, we are a community of data science professionals. We started off a couple of years ago, based out of Mumbai in India. As we speak, at this point in time, we have 8 chapters in India. We are the largest data science community over there. We have one of the most active chapters in Mumbai with close to 6,000 members. I think very important to know is, why did we start it? What exactly is it? So with DataGiri, probably a couple of years ago, we started off a venture of our own where we were building a data product. We were building a product which essentially required a lot of data science talent, and we started looking out in the local pool. We started to look at whom we can hire, how we can onboard at different stages. One of the things that we found is it's very difficult to get the right person. Everyone says that they are a data scientist, but probably I think there is some misnomer of sorts and quite a few things going around. We saw a lot of communities. We looked into a lot of other meetups who were there in Mumbai at that point in time, who could help us with respect to hiring and everything. But essentially, I think we really did not succeed at it. We really had a tough time with respect to get going with that particular product and with that particular talent pool at that point in time. So we really started off to build a community of data science professionals, at that point in time, to solve our problem, to build the product that we wanted to build, and how we can really tap into the ecosystem, and how we can really hire some amazing people who are there. I mean, India is blessed with the demographic dividend. It's just that about how do you find the right kind of people over there. So when we see at that part of the world and some of the other geographies like New York, London, Chicago, San Francisco, we find a very vibrant community, large size communities of data science professionals and generally engineering professionals. But compared to that, something was definitely missing in Mumbai. So we just kind of started off with this particular community, and this was again just to solve our problems, and that's how we kind of snowballed. The way we started this was we reached out to some of the marquee data science professionals and company providing services in that particular space, and the data scientists who are over there, and they can help us bootstrap this kind of thing. And it's just that it has snowballed into something that is has a life of its own, existence of its own, and is doing a lot of good work. So our objective is extremely simple. We're not here to sell. We are basically a platform where we are connecting people on one side to the people on the other side, aspirant population to the practitioners, practitioners to practitioners, leadership to leadership, people at all levels and cadre. Over the last 2 years, we have conducted some really key events. I think one of the highlights was hosting Dr. DJ Patil, who was the chief data scientist in the Barack Obama administration. And I think the key thing over there was, he was on his India tour, and he basically just put out a LinkedIn request stating that he wanted to speak and interact with people across different, cities in India. And we just happened to ping him, and we just showed that this is the community that we have. It is the power of community. It is the sheer size of community and the interest level, and what we had done over there. That is, someone of his stature essentially got interested in what we were doing. Great. We do events which essentially have, learning outcomes. We don't have learning outcomes, hands-on, workshop style, for leadership at all different levels. So we've been doing that for multiple things. Great. We would just like to thank a couple of people over here. We would like to thank Rise Mumbai. Rise Mumbai is someone who essentially, they are our partners in that particular ecosystem, and they are the venue partner, hospitality partner. They help us a lot, and they essentially connected us with the ecosystem over here. Also would like to thank Barclays. Barclays is one of the clients who we count as our clients, in a different space, and they essentially help us to get started. We have a couple of very, very interesting speakers for you lined up. So we have Rangarajan Vausdevan. Ranga, if you could just raise your hand. Fantastic, thank you so much. And we also have Axel. Axel, if you could raise your hands. Fantastic, thank you so much. I am going to introduce them. I'm sure you've gone through the meetup description and already are up to speed with who these are. I'm just going to take some time, just maybe half a minute and quickly introduce them. So Rangarajan Vausdevan, Ranga as is popularly addressed, is the CEO of the DataGiri. Probably you can kind of see it over here. He has 150 member strong global team of talented data scientists, and he's helping companies interested in growing their businesses in big data. He's a big data veteran, including business strategy, solutions, technologies, architecture, data sciences, strong academic background. I will leave the rest up to Ranga to introduce himself, and thank you so much for being here with us. We also have Axel with us, and Axel will also introduce himself, but I'll just quickly give you a very high-level overview. Axel received his Master's in Engineering in Computer Science and Applied Mathematics from ENSEEIHT, France, and MSc in Advanced Computing from Imperial College in 2012. After working for a year in SocGen, he came back to Imperial College where he joined the Data Science Institute as a researcher and a PhD student. He is currently leading development of the OPAL project and finishing his PhD. And he'll be sharing the work that he's been doing with all of us over here. Great, thank you so much for having all the patience. I think I'll just pass on to the first speaker for the day, that is essentially Ranga. A quick a heads up, we are essentially building a very strong network, a very strong global network of educators for data sciences. So in case you believe that you can contribute in multiple capacities, and these are capacities in enumerated capacity, please reach out to me, or please reach out to Shweta. I think we'll also be introducing her in a short time. So if you are a practitioner, if you are a data science professional, and if you believe that you can contribute in multiple capacities, please reach out to us. So I believe we have Shweta over here. Shweta, if you can just quickly raise your hands. I think she's once again zoomed out. No worries. Great. So I think we just have a very short AV, 30 seconds, post which I think we'll just quickly get started with Ranga. Thank you so much for your patience, guys.
Thanks for showing up. Fantastic to see such a big crowd here. So my talk for today has been prepared with a view to both give the newcomers to the data science community what's the practical side of data science beyond the hype, right? And then there's the other side of the coin, which is companies which are looking to attract talent or attract data scientists to join them. What's the kind of problem statement or formulation, or the selling point, right, for the data scientists to join them? What should that be, right, based on our experience, based on having interacted with lots of enterprises across the traditional side of the businesses, like the banking, insurance sectors, and so on, as well as the new age internet era businesses, like the e-commerce companies, retailers, and so on, right? So that's the motivation for this talk. I think a lot of things are open to debate. In fact, it's intended to be controversial. So please feel to just bombard me with questions later on or during the talk. I'm open to that. And also very interested to see what the viewpoints here are. It was my first time to London, first time to see what's the data science community like here. What's the level of maturity, something that I'm not aware of. So let me know, correct me if I'm wrong. I'd appreciate that. Okay, so how many of you recognize this? Yeah, please. Could you shout out what this is?
This is chessboard chessing, tradition chessing.
What's famous about this position? Anybody know?
There's a Kasparov losing some big blues.
You're on the right track. He said Kasparov losing to Deep Blue, but that's ages ago. I guess that's a clue. If you're in London, you see this. DeepMind, anybody?
With machine learning.
Yeah, so AlphaZero. AlphaZero came into use last year. It's a product from DeepMind, a London headquartered company acquired by Google. And then this particular position came about. How many of you play chess? Yeah, don't be shy. I'm an amateur myself. Okay, decent number. So what this position shows is the movement of the white queen. So you don't need to know the rules of chess for those who have not played. So just take it from me that this is extremely abnormal, right? For the queen to actually be here, be attacked by this pawn from the black side. So move over all the way to this side, get attacked by a pawn again, and then move over all the way down to the south. That's extremely unusual. Now the reason that something like this happened was because of AlphaZero. So AlphaZero played against, I believe, the best chess playing computer at that point in time. So that chess playing computer had evolved over a long stretch of time, and intuition and knowledge that a lot of data scientists had put in over the years, over the decades, in fact. Right? And what AlphaZero did was completely kill it, right? To the extent that nobody even predicted that the scoreline would be this heavily biased towards AlphaZero. Now, it so happens that this particular sequence of queen moves was even appreciated by the grandmasters. These are the top playing gods of chess, so to speak, right? Because they never thought that something like this would be possible for a computer to learn and play out. And the most astounding piece of this, I mean, here's where the hype comes in, right? And I want to construct the hype so that I can demystify this. So the hype is that this particular computer, AlphaZero program, it didn't know anything about chess 4 hours before the event. Right? Up to that point, it had known nothing about chess. It didn't even know the rules of the game. So I think just about the time when the event was supposed to kickstart, it was given a whole bunch of these positions of chess boards like this, and told whether it's a win or a loss or a draw, right, for white. Right? And then it used to take that information and train itself and figure out what the rules of the game are. So the rules of the game were not told to it explicitly. It actually figured it out automatically. So that's quite astounding, right, if you think about it. But then that's where the hype stops. Like, the reason why it stops there is here, it's a very well-controlled problem statement. So by that I mean, it's a constrained problem statement. You don't have weather affecting this. You don't have left hand versus right hand affecting this. You play the same chess. You don't have extraneous circumstances coming in, making an impact on the game. It's just black versus white, right? It's as simple as that. So where does data science go beyond the hype? So one of the things that happened, it seems like, since not many people in this audience are aware of this kind of a development, I'll just elaborate a bit on this. So there was tremendous media coverage on where AI was headed, right, because of this particular development. And simultaneously, there's also been this movement towards driverless cars and so on. I'm sure all of us are aware of it from popular press. So if you look at both these problem statements, they're all well-constrained problem statements. You might think the drive is really hard, but actually, it's much easier than running a bank, right? Much easier than running a shop. So the reason why it's easier, because there are only certain constraints within which the driving happens, especially in a developed nation like UK. In India, it's a different ballgame altogether. Right? So given these constraints, can I learn to behave as a system, as an autonomous system? So that was the problem statement for driverless cars. For chess, it's something else. I'll give you one more piece of astounding information again. So the same engine that learned this also learned to play Go. Go is another game. It's much more complex than chess. And there's a Japanese version of Go, which is even more complex apparently, not that popular. And it beat the top Japanese Go playing engine, again, without being taught the rules. The same engine. Right? So that's even more astounding, right? To think of it that whatever learning it had from this particular game or from this particular event, it actually translated all of that learning into a completely different setting where the board looks different, the rules look different, and so on and so forth, but still one game. comfortably. So the hype was that a lot of things that we do as human beings could get automated. And here was a problem statement where it's supposed to be mentally taxing, it's supposed to be extremely heavy for somebody to actually pick up as a game. And like as a child, I used to do this all the way through school, through college, and eventually became an amateur. And this thing took 4 hours. Like it's ridiculous, right? But then again, that's where the hype needs to be deconstructed. Let's move to a completely different setting. Let's say you're a bank like Barclays or Lloyd's. What happens within the bank? We all know, we're customers, we've been frustrated, we've been sometimes satisfied, we've been happy at the kind of products we get, but more often than not, we feel we've been ripped off. But most of it, if you really think about it, it's because there hasn't been an effort towards personalizing service or personalizing the products of the bank to what we think we really need, right? We might need a particular type of mortgage because we believe that that helps us meet our life goals. And if the bank can understand that thought process behind us, right, behind that need for a mortgage, they can actually make a much better job of giving us what we want at the price we want and making us feel happy, right? And the way that happens is using AI again. But that AI, that machine learning, is very, very different from what we saw before. It's very different from playing chess, very different from driving cars. And that's the beyond the hype segment of the talk that I want to give. Like, so the rest of this talk is going to be about this. Like, what is data science beyond the hype? Don't get misled by things like automation. Don't get misled by data science being the next cool thing, machine learning being like this all-conquering power. Actually, it's not. There's a lot more practical things that you need to worry about before you get to like really relax your mind and think about the future when we don't have any role to play. So let's take a look at this a bit more and see what happens within this. So if you look at this bank, a typical bank like this does a whole bunch of things just to get customers like us happy. So let's talk about credit cards, for instance, right? Every single credit card that goes through the system, every single swipe that happens, right? It could be at a local shop, it could be at a travel agent, it could be on Amazon.com. Every single transaction is evaluated for fraud. I mean, we all know that. We've got calls now and then to say, Mr. John, is it you who's actually in Sweden buying something shady, right? So that transaction fraud checking algorithm is a machine learning algorithm, right? In the days past, it used to be what's called as rules, business rules. So one example of a business rule would be it's impossible for somebody to be in Sweden and London at the same time, or within an hour, right? It takes that much longer. That's an easy rule. But a more complex example would be something where let's say it's actually 2.5 hours separated between transactions in London and Sweden. 2.5 hours seems okay, right? Maybe it's possible. Maybe it's airport to airport. Then you start to look at geographic location. You start to do reverse engineering of where the transactions have happened. Put it into a model to say the model is throwing out a number, and the number could be some kind of a score that says that this transaction is suspicious, and then that triggers a call from the operations team into your phones to say that it's you who actually made the transaction. So that's an ML model that runs behind the scenes. Now, let's say that you call in to complain about your favorite product, right? And as you complain, they figure out that you actually need something else, and they give you the best price for it. Maybe you're complaining about a particular fee transfer because you sent money home, and that costs too much money. So they come back and say, look, I know you're really frustrated by this, let me give you a better price. And then you say, if you give me a 10% discount, I'm okay. And they know that already, right? And the way they know that is actually using machine learning again, right? So that's a model that's running behind the scenes. Let's take a look at this particular segment. So here's a person who jogs a lot, right? He's a physically fit person. He's shopping online, no connection to this bank. But as he shops online, we know from partner relationships between this e-commerce company and us that this kind of a persona, like the athletically fit person, is actually looking for something interesting, maybe a shoe or maybe an athletic wear. So should the bank push for a specific type of color for the shoe, right, through this partner establishment? Should it push for a pink shoe or a blue shoe? because that's more likely for him to convert. And when he converts, guess what? He's going to use a card, or he's going to make a transaction on the bank's network. And that's how the bank makes money. So that's indirect, right? It's very different from the direct conversations we've had so far. So it's indirect. That's also possible. That's also something that's controlled by a machine learning algorithm. In fact, if you want to be more specific, it's something called as A/B testing. Anybody heard of it? Yeah. Cool. Yeah. So that's A/B testing that the bank could do. And then there's a whole bunch of these really, really important people. Right? They come in, they ask all kinds of questions, they expect answers immediately. Sometimes they don't even wait. And if they don't wait, you know there's a problem there. There's penalties to pay and all kinds of things. So that's the compliance side, especially with GDPR. This is getting really nasty. Right? So that's this piece here. And they need to be serviced as well. And then there are these reports to the executives. The internal stakeholders who make decisions, they are the important people. They actually get to know what's happening across the bank. They make some calls and so on and so forth. And these reports, invariably, in practice, are last minute. They never planned. Right? They never happened like 1 month ago, and then you actually plan for it, and then you can deliver on time, and you take a coffee or whatever. Right? It doesn't happen that way. It happens that morning. They come in at 9, they want it immediately, 9:30, the answer has to be ready. Right? So these pieces, reports, compliance, they don't use machine learning, but there is actually a strong role that machine learning plays in order for you to be able to service those needs. The last team that I wanted to talk about is this team that manages the entire infrastructure. They keep it up and running. They make sure that every single thing that the bank relies upon for its critical operations is actually able to happen in the first place. So this is the IT team, or operations team, or whatever you want to call it. They're in charge of keeping this entire thing running. So look at what's happening here. Everything is actually centered around a data platform. Now, if you write machine learning code that plays chess, that particular piece of software that we talked about in the previous slide, AlphaZero, was running in a mammoth machine. Mammoth meaning the likes of which used to be compared with supercomputers in the back in the day. They create supercomputers. For those who are in IT long enough to have lost hair like me. Right? So create supercomputers, that's the comparison. A mammoth machine dedicated only for playing chess. That was AlphaZero. Look at this. Right? It's one platform that serves all of these machine learning needs, also serves the bank executives, also serves compliance, also serves the team that actually keeps the platform ready. Because every time these guys do an upgrade, they're going to take the platform down. What happens if they take the platform down? Everything else suffers. Right? So the data science beyond the hype is machine learning is a very, very small piece in the grand scheme of things. Like AI is a very, very small piece in the grand scheme of things. In fact, it's so small that it's this black box that you see here. Right? So this is a paper that Google published, which talked about what is required for machine learning to be realistic, to be of value, right? To be something that businesses can benefit from, beyond just playing chess, beyond just driving cars. And what they found out using their analysis, the reason Google keeps coming up again and again is, of course, they are the torchbearers of many things AI. And there are few tech companies which have done this, like Facebook, Microsoft, Amazon, and so on. But not many of us actually know or have that kind of experience. So the good guys at Google have actually published a paper for this. That's fantastic. So we all benefit. So the ML code that's here, it's a very, very small piece, right? Compared to everything else that needs to happen for this ML to be of value, right? So if you build a data science program, let's say that you're training to be a data scientist, I think you could get away with the impression that data science is the next big thing, that AI is the next big thing. Certainly the case, right? Because if you look at this slide, almost everything else has been talked about before, has been innovated on before, has been addressed as an area of research in academic institutions before. So certainly ML seems to be the flavor of the day. But then again, you graduate from this kind of a program or you graduate from university, in order to be able to apply your talents into something that really is of value, it's extremely important to actually understand what's happening around it. If not, actually do it yourself, right? be able to do some of these boxes of activities by yourself. I think that's the message I wanted to really leave, like all of you in the audience. In case it's obvious, apologies. You can take debates after that. But in case it's not, I think that's the message I wanted to really convey. So let's go through this one by one. Like what all happens when a machine learning code goes into production. Production meaning it actually impacts the business in a way that's tangible. Let's start on the left, right? So the size of the box is proportionate to the effort that typically goes into doing those things, right? And it's not for lack of automation. Let me put it that way. For those who might have heard of DevOps anybody? Yeah, cool. So DevOps looks to automate a lot of things around how code goes into production. So these boxes are there despite DevOps. So despite attempts at automation, right? So there's a significant amount of importance, right, that each of these boxes have. Let's go through one by one. So configuration is as easy as it sounds. Being able to configure things like software, hardware, things like applications, and getting that right turns out to be an extremely draining task. It's not something that's easy to automate. It's not something that you can actually learn as an algorithm. Potentially, that could be one of the applications of machine learning in the long run. But today, that's done human. That's led by a human or a team of humans, right? So that's an important task to actually be able to figure out. Let me make it more concrete here. So let's say that you came up with a machine learning algorithm that predicts fraud. How often should it run? Any guesses? How often should machine learning algorithm that predicts fraud on every card transaction, how often should it run? On every transaction. That makes sense. What about the Think of Blue experiment? How often should that model run? Okay, so there we'll have to break down a bit more. So does it need to run every transaction? Not really. How often should it run then?
Whenever there's an option.
Yeah, whenever there are options available for the customers to actually play with. Let's make it even simpler, right? What are you looking to do when you say something is pink or blue?
Recommendation.
Yeah, recommendations to try and get somebody to buy something. So you don't need to do that experiment too often. Maybe you do it once in a while, maybe you do it once a week. You go back and change things and come back again next week and put it in. So that's a configuration setting, right? That's something that you can explicitly tune and say, look, I don't need this machine learning to run often. But that's a call that you who wrote the machine learning code in the first place have to make. And how do you make that call? By understanding the business, understanding what's actually going on from it, right? So that's an example of configuration. Let's get to a few more things. Feature extraction. So that turns out to be the most time-consuming task in the pipeline of data science. And I'll have another slide that shows the pipeline of data science, but this feature extraction and a couple of others, they're all up there in the upper echelons of time-consuming tasks in data science. Right? Machine learning is not that. It's not the art of coming up with an algorithm. That's a very small thing. Right? It's actually the feature extraction. It's being able to extract signals from the data. Like to put it even more simply. So in the fraud example, what aspect of that data constitutes fraud? It's not something that we can easily intuit upon, right? Please.
There's sort of viewing this as the majority of time is actually spent cleaning the data. Is that also in feature extraction, or is that somewhere?
Yeah, that's a great point. So, in fact, that's these other boxes I was going to talk about, but they're all roughly the same size. I guess I have parallax setup, but yeah, they're all roughly the same size, right? So, data cleansing is, of course, one of the other tasks that spend a lot of time on. So, let's come back to this feature extraction. So, what are the features or what are the signals in the data that constitute a feature for a fraud model? Is something that we can actually guess, right? Like for instance, the location example we were saying. But there are other features which we don't know anything about, which could be something that the machine learning algorithm picks up on, right? But in many cases, it's us who are writing the algorithm who need to understand the business to be able to actually say what features are important. So there's a tremendous amount of time that's spent here. The other part, which is even more significant, like you don't have machine learning if you don't have data. So data collection becomes an issue. Now, it's fancy to actually be able to collect data from a website. And it's actually not that cool because it's actually done. It's a done problem, enough open source technologies. But let me give you the bank perspective. A bank being a legacy institution which has grown over a period of time. most of these data sets in these institutions reside on proprietary old school databases. These databases are so old school that they don't want data to leave the databases. They put a protective wall, right? They say that no data goes out unless you ask me, the entity, the supreme owner of this database. How do you collect data from there? They'll tell you that you can buy more tools. You can buy more expensive software to be able to actually get the data out in the first place. But what if you don't want to buy all that software and invest all that money? How do you collect data? So that's an important question you'll have to answer when you start to look at machine learning in that context, the legacy context. Right? So data collection is something that we spend a lot of time on. I'll give you an example of a practical problem for this. So if you look at sourcing transaction data, so let's say that there's a transaction processing system that's just recording every single credit card that ever came in. Being able to tap that data and be able to take the data out into your algorithm is fairly straightforward. Let's go to another version of this problem where the customer has a table inside the database where the person is updating things like address, phone number, and so on. You move locations, you go to the bank and say, let me update the address. Now, if that source database is not storing what was your previous address, so let's say that you updated your address and it updated in place, meaning that your previous history was deleted because of this in place update. How do you run a machine learning code for the previous version of you? Right? So you did a transaction a week ago, you updated the address now, you come back tomorrow and say that that transaction was never done by me. How does the bank refute you or agree with you? They need to actually have an understanding of what you were a week ago. Right? What was your address the last week? If the source database was not capturing that information, nothing that ML can do can actually figure out that you were living in some other place a week ago. So data collection becomes a critical challenge in order to be able to tap the data or the version of the truth that used to exist at that particular point in time. That's a very key piece that you have to spend a lot of time on. The next piece is data verification. This comes back to this gentleman's point on data cleansing, right? So how do you verify the data is right? I'll give you an example. So we were given a problem statement to predict, or rather build an algorithm to predict that a particular product that goes down the assembly line is faulty or not. Right? Does it have a defect or does it not have a defect? So the business leader who spoke to us, he said that we believe that AI can play a critical role. Deep learning will help us here. Can you help us out? So yeah, sure, of course. So we start working with them, and then they give us the data set. And it turns out that 2 weeks later, 2 weeks after we've begun the experiment, we figured out that that person who gave us the data set gave us only the data set of defects. Right? So we didn't know that. Like, we knew that there were going to be these data sets that we have to actually design a data processing or data preparation or a feature extraction pipeline for. We started doing that, and 2 weeks later we had a chat with him to say what are the classes of, what are the labels for these data sets that they've given us. He said, oh, they're all defects. What's the point? So then it becomes extremely challenging to convince him that it's not the defects that's interesting, it's actually the good part that's interesting for us. Right? It's actually this mix of both that's interesting. So he comes back and says, but why would we be interested in the good part? Because I already know what's good. I'm only interested in what's bad. And amongst what's bad, I know that these things become bad only once a day. Like, one part, every million parts in a day. Like, so I've done so much work for you in collecting these 10,000 samples of bad things over the course of last many days and giving you this. So it becomes almost defensive. But that's data verification. You actually have to understand what the data is about. And there's a lot of time that's spent there. And in legacy systems, you would find that these kind of issues occur again and again. So for instance, the same address example. In the previous version of the database, maybe they didn't store the second line of the address, but now they do. How do you reconcile that? How do you actually put it all together? They didn't have the landmark before. And the landmark was of very, very significant interest because that's a point of interest for you. Right? So all of that is data verification that you spend a lot of time in. Let's take a look at what happens on the right side. This is all regarding what we call as machine learning serving, like machine learning model serving. So for those of us who have done data science extensively, so a biggest portion of effort is in what's called as a serving infrastructure. So that data platform, which I drew as a single box in the previous slide, is actually this mammoth serving infrastructure. In the AlphaZero case, this was a supercomputer, right? This big box that you see here. But in a more legacy kind of a setting, like a bank, this would be a combination of a whole bunch of data warehouses, a whole bunch of data lakes, Hadoop, and all those really good terms, right? So all of that is actually going to be here in this serving infrastructure. So if you don't know whether your serving infrastructure has a certain kind of capability, you're not going to be able to write certain machine learning code at all. So I'll give you an example. So anybody knows what's the critical component that can speed up deep learning? In terms of hardware. GPUs, exactly. Right? If you didn't have GPUs and you had to process a lot of images, it could take a long time. Right? So if you didn't have GPUs, there wouldn't be much of a point trying to train a deep learning model on very large data sets and have it be completed within a period of time. So serving infrastructure becomes an extremely important thing. An associated piece of work that needs to happen is machine resource management. So what this means is you have to understand how do you parallelize algorithms. So let me give you again why this is important. So many data science or university courses which talk about data science, they talk about how you can apply libraries of algorithms, linear regression, clustering, supervised learning, unsupervised learning, and so on and so forth. But almost all of them depend upon a library that's available easily. It could be Python, it could be Java, it could be R, etc., etc. Right? What if none of those algorithms was good enough for the problem statement that you were doing, but you still had lots and lots of data to actually tackle? Then you have to think about how do we take the logic or the functionality I want to achieve, which is clustering as an example, right? How do I take that and parallelize and distribute that across a bunch of machines? Why is that important? Because you want to actually train your model very fast. So one of the earliest pieces of work that I've done was helping out LinkedIn with their people you may know recommendation. So every time you log into LinkedIn, there's a recommendation that's there. So in the early days, I'm talking back in 2008, 2007. Right? So we worked very closely with them. So for them, the ability to parallelize really dictated how quickly they can make recommendations to you that's very relevant. So for instance, if they keep recommending the same person to you again and again, even though you've already rejected not wanting to connect with them, right? Then you get frustrated as a customer. So what if they can actually figure out more and more members of your network very quickly? Then you really get hooked on. You start to think, like, what is it that they know about me that they actually can predict whom I want to connect with? Right? So the ability to actually get there, the agility of the business comes down to how quickly you can train the model. But that comes down to how much infrastructure you have and how much of an understanding you have of what machine resources are being used by that machine learning model. So it's very important to understand what's going on behind the scenes, underneath the hood, like all those fancy phraseology. So take one of those libraries as an example, or scikit-learn in Python. What's going on underneath? What if I wanted to parallelize certain algorithms within scikit-learn? Those are the kinds of things that you'll have to think about once you get to some of these big data problem statements. Then you have process management. So process management the box is actually somewhat the same size, I guess, but slightly smaller. But it's an extremely important thing. If you go back to the bank slide, there are 6 or 7 different things happening at the same time on the same serving infrastructure, right? Same data platform serving all of these things. Let's say that your code now suddenly starts taking 80 or 100% of all the resources. It could be because there's a bug, right? There's a bug in your code, or you didn't anticipate for so much effort being going into model tuning or model training. So what will happen as a result is somebody else's code is getting affected. Maybe there's another model, like the cross-sell model or the fraud model, which fails because your code actually takes a lot more time. So what happens then is some administrator there, the good folks in the IT crowd, we saw in the previous slide, they start to kill your jobs. Or they start to actually control or throttle how much resources you actually have. That has an impact on what you assume in terms of algorithm design. So I'm getting a little technical here, but bear with me. So this example, I'll give you an example of what happens in this problem area called reinforcement learning. So the example of alpha 0 that we saw is a technique called as deep reinforcement learning. So in reinforcement learning, you explore a space. Let's say driving cars as an example. So you drive down, you figure out that there's a concept of a lane, there's a car that's right in your blind spot, and you use that as information to tune the way that you drive. But that's dynamic, because in the next second, that car is no longer in your blind spot, it's actually sped away. Right? So reinforcement learning allows you to react to these situations dynamically. Right? But in order for you to react to these situations dynamically, you're making an assumption that you have enough compute power. You have enough machine resources to be able to react. What if you don't? Right? What if some other process that your colleague wrote ended up killing or throttling your algorithm? Then your reinforcement learning approach might actually not be effective at all. And the business will see that this particular type of fraud was not captured by your algorithm. They'll come back and blame you. So your code didn't do its job. So then it becomes a question of actually understanding what else is running on the same platform. So process management becomes an extremely important thing. It's tied very closely with machine resources. The last piece here is analysis tools. These are the likes of visualization and so on and so forth. Monitoring is a critical piece. Normally, data scientists don't spend too much time looking at monitoring, but this is something that's very critical for production-grade infrastructure. So, landscape of things that happen around your ML code. So, it's something to be aware of. So, what do you do as data scientists? Of course, you actually train yourself in everything that's data science in terms of libraries, in terms of things like feature extraction, data cleansing, and so on. But what's more important is this top right corner here, right? Which is this process of data science itself. Being able to understand what is the business process that you're actually optimizing or building a model for is an extremely important thing. And in what context does that problem need to be solved? Right? What are the other things that are ancillary to the problem statement? So all of that is a very important piece that actually needs to be considered when you build an algorithm. You're not operating in silos. I guess that's the message there. Right? So one important thing that you have to think about is when you deploy these models, what is it that the business is actually getting from it? Like, is there an actionable insight? In the case of fraud, it's extremely apparent, right? Obviously, you're trying to stop fraud. But what if you were doing website analysis, like clickstream analysis? What are you looking to do by analyzing all the number of users who came to the website, did this, and then finally signed up for a credit card? Why is that important? I think you'll have to answer that question yourself, because data science is not the answer. You actually have to tie it back to the business in some form. There's a layer of interpretation that needs to happen on whatever it is that you're building in terms of data science. So again, an example here. So the same problem statement of detecting defects in the assembly line, right? So that problem statement is something that you can solve using deep learning. So there's a particular class of deep learning networks called convolutional neural networks, specifically RCNNs. You can use that to solve. But how do you explain that to the business? You'll only be able to say good or bad. But in order to be able to explain is where the business actually gets an insight. So you have to think about these kinds of problem statements as well. Can you explain the business can actually action upon those insights? So I've been told I'm running out of time, so let me just go through quickly. So if you think that automation is one of the hype terms, I can tell you that data science itself is getting automated. Right? So let that sink in. Data science itself is getting automated. So if you do a course on data science, maybe in 5 years' time or even lesser, most of these things, most of these steps that you do in data science is getting automated. So what are you learning then? It's a question that you'll have to ask. So if you look at the process of data science very quickly, so data collection, we talked about it, profiling and so on and so forth. On the left side, you see research as well as commercially available products, as well as open source products, which are taking a crack at automating each of these different steps. Right? So, but there are places where there are question marks. Like, so those are where data scientists have to play a role. Right? Those are where data scientists actually have a tremendous ability to actually cause an impact on the business. These would be things like hypothesis generation. What is the problem statement? Like in the case of fraud, we knew exactly what we wanted to build. But what if you didn't know that it was a fraud problem, it was something else. So generating the hypothesis that makes sense to the business is not something that automation will play any kind of a role in the near future. Right? Feature engineering. What features are important? What signals are important to unearth? Notice that in certain domains, even this has been automated. The case of chess as an example. Right? AlphaZero has actually automated the need for actually creating features. You don't need to do it anymore. But that's a constrained problem statement. What if you actually generalize this? Feature engineering is still open as a problem statement. Last part is insights validation. How do you validate these and tie back to the business? But pretty much everything else, there are techniques available for automating it. So that's an important thing. So if you take away some things from this talk, right? One is data science is a lot more than just cool, popular AI, and that's the hype side of it. You go beyond this. So if you had a chance to choose a particular kind of company or a particular kind of project that you want to work in, given that data science itself is getting automated, it's not important to learn how to use an algorithm, but actually what happens behind the scenes, what are the assumptions, right? You would want to choose the business context more than the tool of the technology. So TensorFlow is great, but you wouldn't choose a project because it's TensorFlow. You would choose it because there is some business value to it, right? Likewise, choose operational platforms because that gives you a complete understanding of what happens when you put machine learning into production. Not some experiment that you do once in a while and you don't know what's actually happening to it, right? Choose a process or methodology as opposed to specific algorithms. Like random forest, it's not that important. Like what's more important is why random forest, or why not something else? Why not naive Bayes? Why not support with the machines or whatever, right? So the process of actually figuring that out is a lot more important. I'll give you an example. So naive Bayes as an example. It's a specific type of classifier, but its fundamental assumption is the inputs to the data, inputs to the naive Bayes are not linearly dependent. And that's an assumption that the designer of naive Bayes, the algorithm, made. If you didn't know this, and you gave an input data set which had linearly dependent variables, you would get the wrong result. And the worst part is you wouldn't know, right? So it's more important to pay attention to the process of the methodology than be stuck in one specific algorithm or a library. Choose mentors. I think mentors are a lot more important than the brand or the salary or whatnot. And this is something that I personally have struggled with because as a bootstrap company, we have to fight the salary battle all the time. So we instead say we have the mentors to actually help you out. And then learn fast, apply fast, and so on. Cool. Thanks. And be right back. Sorry.
All right, guys. So just to get a sense of this, right? We're doing an event in London for the first time. We've been doing a lot of events in India. So just want to understand, like, how many of y'all here are from data science? Like, if you can just do a show of hands, like, how many of y'all are working in this space and are more and more involved? And then I would like to also understand how many of y'all want to learn more about this. So for future events, that just gives us a perspective on things. So first, how many of y'all involved very deeply in data science here? All right. And people who want to learn more, keep learning more. All right, perfect. Thank you so much. So the next talk is by Axel. And thank you.
Hello everyone. Can you hear me? Great. So thank you for having me tonight. I'm very happy to be in front of such a large audience. So tonight I will present, so I'm Axel Oehmichen, I'm part of the Data Science Institute. I'm actually writing my PhD. So wish me best. And this is some work I've been carrying out with a couple of colleagues over the past few years. So interestingly, the talk you just had couldn't be better introductions for what I'm going to present to you, because it's exactly what the data science pipeline looks like. And all the problems, all the different parts that have been described, we have had them. From collecting the data to processing the data to creating the data to cleaning the data to monitoring what's going on. I mean, the whole stack we have been through. I will not present every single problem we have had. I will just present the data science part and the analysis we have been carrying out. And in this context, we looked at how to assess political fake news on Twitter. So, what is fake news? So, I've been to Wikipedia, just as every student and teenager would do, and looked at the first line of the definition. So fake news is a type of yellow journalism or propaganda that consists of deliberate misinformation or hoaxes spread via traditional print and broadcast news media or online social media. It doesn't help. So the first thing we have had to do is define from our perspective what is fake news. We have seen a proliferation online. So, I mean, the Oxford Dictionary has defined, I think that's 2017, the word post-truth as word of the year. And I mean, we have had comics on the topic. I've had some robots which came in on the forefront during the 2016 US election, Donald Trump, which I hate so much now. And Yahoo News and so on and so forth in terms of all kinds of news that have been propagated through internet, TV, whatever you can imagine. How do you define fake news, as I said before? A bit of background before on what we have done. So the first thing we have had to do is collect data on Twitter. So to do so, we made the first choice. We couldn't collect all of Twitter. That wasn't possible as much as I wanted, as much as Data Science Institute has money for infrastructure. I was kindly told to restrict a bit the search and not collect everything that was going through the internet. So we first selected 4 keywords, so 2 handles and 3 keywords, sorry, 5. So 2 handles are 3 keywords during 5 months, so November 2016 to March 2017. And only those 2 handles and 3 amounts to, and this is sample. Keep in mind, Twitter doesn't give you everything. This is already sample, so this is only a fraction of what's going on Twitter. It already gives us 57 million tweets. To give an idea, this is roughly 200 gigabytes of data. If you wonder if you can store that on your computer, the answer is yes. Can you process it? Definitely no. From this, we have selected 9,001 viral tweets from the selection. So that data set is freely available if you want. So you will be, once we have my presentation, you will be able to download it and play with it. And we define viral tweet as more than 1,000 retweets. So that gives us a fair indication that the audience is broad enough to be considered viral. If the only person that sees your tweet is your grandma, that's not of much impact. So the first decision we've had to make is what is viral. We have put that threshold, it's arguable. It gives us still a decent size data set to work with, so only a few percent of the total size, but it's more than enough to work with. Why? It's because once you have those 9,000 tweets, you need to label them manually. So those are some of the achievements we have done. I will go over them in the next few slides. And the first thing, once we have collected the data, was to label them. So to do this, I basically collected and cached all the IOUs that people owed me and gave them chunks of tweets. So I personally went through more than 4,000 of them. Not the best week of my life. Definitely soul crushing. I don't recommend. But something very interesting came out. So this project was carried out with 2 other colleagues, as I said, mostly. So the first data set was labeled by actually students. So students and various people, so friends and other colleagues, other people's departments, undergrads, everything that basically I could ask to do some. And the others were done by myself and my 2 colleagues. So the first thing we noticed is how we didn't tell them anything. We told them, okay, so actually we told them a few guidelines. If it's fake news, non-fake news, and then no. And then basically being, for instance, a tweet that is haha at Donald Trump and a URL that is nothing. So that was viral at the time, but then when we traced back, first problem is the URL no longer existed. So that's the first problem that we got, is some of those tweets we couldn't trace back the history of the tweet, what was going on, why it got viral, because Twitter actually shut it down, identified as infringing Twitter policies. And for us, it was impossible to actually see what was happening at the time. So we collected the tweet at the time. We collected actually a bunch of other tweets like this. And you can see that out of the 9,000, 4% where we couldn't possibly classify them for various reasons. Impossible to trace back what was said or what was shared. Impossible to actually read it. So we collected some Arabic, some Russian, Chinese. So Imperial is great to have a large variety of people, but still Russian is not that easy to figure out what the person was trying to say. And Google Try doesn't make it easier. So that actually took around, between the collection and labeling, it took already 6 months. So 5 months for the collection, 1 month for actually labeling all of this. The second thing you can notice is how different the 2 labeling are. What we notice is people with various levels of knowledge of American politics, of American culture, had a very different perception of what was fake news. The other thing is the tolerance toward bias in the way the situation is presented can be very different. So I have a lot of Chinese colleagues, and some of them have a very high tolerance toward what is defined as true or false, meaning the scale between the two can be a bit skewed in certain instances, or a very different perception at all. So when we discuss why did you label like this, their explanation was we could understand that their perception is very different from ours. So in this instance, that was the first problem we had to face with, was how to deal with all this. So even though we didn't use the first set of labels, it still gives a very interesting insight on what people perceive as fake news. The second thing that we got and that we noticed was a huge skewness towards 2 points. So there's 2 ones, which are election night and the day after the election. So we were very happy at some point when we were doing some analysis and said, oh yeah, so people propagate a lot of fake news during Tuesdays. Well, half the data set is on Tuesday, so up to that point, it makes sense. So this is another thing you have to keep in mind. It's not because your analysis tells you something that it's ground truth. So in this case, we have had to discard that feature when we were doing some feature selection to, as I said, identify fake news and extract features that would indicate that the tweet has the potential to be a fake news, is that kind of skewness in your data set. Here, it just turns out that people were a lot more active during election nights and the day after the election than any other day before or after. And because of that, we have had to remove that feature from the one we selected for building our model. So as a data scientist, you have always to keep in mind what you're dealing with. Is it human data? Is it biological data? Is it financial data? Do you have that kind of skewness in your data? Do you have errors? Do you have people being mischievous on purpose or messing with you for XYZ reason. The second step was to then select from all the features from Twitter, meaning when you look at a tweet has actually a lot of metadata. It has location data, it has a number of favorites, number of users, followers, is it a verified or not verified account, how many hashtags you use in a tweet, how many mentions, how many friends, how many media you share, and so on and so forth. So all this, when you collect a tweet, is given to you by Twitter as well. In order to select those features to see if there is a statistical significance and statistical difference between fake news and non-fake news, we use Cognover Smirnov, which I'm sure people doing statistics here are fairly similar, familiar with it. And we decided that any p-value below 0.01 was significant. There is no, so another thing, there is no actual literature to tell you what p-value is significant. And everyone telling you otherwise is bullshitting you. So in life science, so part of my background is, and part of my PhD is in life science. The common agreed p-value is 0.05. And the reason behind it is because the first guy publishing on the topic decided, as any decision, as we did for virality, to choose 1000, that 0.05 was good enough. And that's the story. That's literally the reason behind the 0.05. In our case, we chose a lower value to make sure that the significance is, and the confidence we have in the features is much higher. But basically, if you want to go say, okay, I will select only what is below 0.001, there is nothing preventing you from doing so. The second thing we looked at is time-related features. So those ones are the propagation of the tweets. How long did it take for the tweet to reach 10, 20, 50, 100, 250, 500, and finally 1,000 retweets or favorites? The interesting part is the patterns of propagation are different between the two. So if you look at MIT's recent publication, what is interesting is when we looked at this and we looked at what they have published few weeks before us, we don't agree. So in our context, with what the data set is telling us, is that in our context, fake news propagate faster than real news. This is what my data tells me. In their context, it's the opposite. So you're asking me, so now why? The reason for this is, in their context, they look at the broad scope of propagation of tweets, not just political fake news. And actually, I'm pretty certain, they haven't shared the data set, but I'm pretty certain if we extract from that data set the same type of tweets as we have done in the context of political fake news, we would have similar results. So again, you have to understand what the data scientist is trying to achieve and what the data is telling you, but make sure that not because MIT says, okay, propagation is faster for non-fake news, then you are wrong. That's not the case. We are not looking at the same thing. So another thing is this, is when you actually look at results, to be extremely careful to always put in context what you're looking at. We continue, so all these were features given to us by Twitter. So either through history of tweets, because we have collected so many of them. So to do the number of retweets, we actually had different collections at different times. So this is how we could trace from 20, 50, and so on and so forth. And the others were given as part of collecting the tweets. So they are natural, if I may say so, natural features. Once we got all this, we wanted to have more features to make sure that we don't miss anything and that if we could derive new features. So to do so, we first started with natural language processing. So we did two types of analysis. First is sentiment analysis, and second is textual features. So for sentiment analysis, we did two different of them, lexicon and machine learning. I will go into more details. And for the textual features, we just extracted different bits from the text, so either from the users, from the text, from the username, all kinds of text we could find as part of the metadata that was provided to us, and not only just the text. In this context, for instance, we realized that the username that has caps or weird character is not scientific term, but it describes characters like exclamation points, question marks, so on and so forth, had significant chances of being people propagating fake news. So a bunch of others were literally just noise, but it's still interesting to see that there are still some key features that people would think, like capitals. If you see like, I don't know, ABC capital underscore I am angry exclamation point, probably a troll. And this is actually, so with an unbiased view using just regular expressions to capture that impression that we have. So we then carried out sentiment analysis. So the sentiment analysis describes core sentiments that exist. So you have 7 core of them, and 3 non-core, which are trust, negative, and positive. I'm not sure if you can see properly. All these core sentiments are very similar to one another, in a sense that from data that we got, only a few of them are very different between fake news and non-fake news. So you can see that non-fake news usually are more positive, while the fake news ones tend to be more negative and a lot less positive, of course. Can anyone explain why? There is a rational explanation behind this.
What was the question?
Why fake news tend to have less positive sentiments in a tweet and more negative ones?
Because people act more out of fear than out of happiness.
Exactly. So one core sentiment that always comes out no matter what sentiment analysis you do is fear. And fear is part of the negative sentiment. So it's positive and negative are actually an aggregation of all the other core sentiments and belongs to one another. But fear is usually how fake news instigates and how they why they propagate. So in our case, faster is fear. So again, the data is saying is something, but we always go back to why. And every step of the way, we say why, why, why. If there is no clear reason for this, we still keep it, but it's not very satisfying. And we always keep or try to do additional analysis to make sure that what we have is indeed ground truth. As I said before, the virality, even though it's highly significant, it's absolutely not usable because of the structure of the data. The other analysis we did was same as before is temporality evolution of the news. So fake news tend to be messy, to say the least, while non-fake news tend to be held in a lot more deterministic way and to have actually global trends across the board. So we didn't derive any feature from this, but it was a confirmation for us that definitely there are underlying differences, at least in core sentiments, between the two. From these naive approaches, we moved to a more elaborate kind of techniques. which are machine learning approaches. So not just lexicon approaches, which are basically I am angry, this is a word, it's related to a core sentiment, and I basically weight all those words together to give a sentiment on the tweet. And you pile them up like this, and it gives you a final score. This is the core idea. Basically, every one of you could do it manually. Basically, the lexicon approach automates that effort for you. You have other ways to do sentiment analysis, which are word-to-vec and fast text algorithms using word embedding. So again, unfortunately or fortunately, word-to-vec was developed, if I'm correct, by Google, when fast text was developed by Facebook. You have publication on the topic, each one relates to one of the topics. They are fairly recent, meaning they are less than 5 years old. They are very interesting because they allow you to approach, to give a whole new approach to not just dictionary approach to base sentiments, but to have a mathematical approach. So I'm not going to dwell into too much details because they are fairly complex, but once again, you can see that there are different trends even between the two. I will go into more details for the fast text. So we pre-train the algorithm on Wikipedia. So we use Wikipedia database as input for the fast text algorithm. Once we have computed the associated vectors for each word, we then do the same for each word in a tweet. And from this, we obtain 2 final vectors for each tweet with a mean and standard deviation for each one of them. So the problem with this is you end up with 2 vectors of dimension 300, which is a lot too many features, and actually most of them are not contributing features to the models. So we use the standard technique called PCA, Principal Component Analysis, to project and reduce the dimensionality of those vectors. Once this transformation was done, using the elbow method, we selected the highest contributing features from those resulting reduced set of features that we extracted from the PCA. And now, if you have a headache and have troubles to follow, that's normal. That's months of work for 3 people. So I'm trying to give you an insight of what the data science pipeline looks like, but don't be surprised if you are not grasping every single bit. I'm more than happy to discuss them with you afterwards. But yeah, this is complex. This is a lot of steps. This is a lot of, what I'm skipping is a lot of failures, a lot of optimizations that we have done as well. So this is because you have different parameters. So you need to do parameter selection, which I will describe a bit after. But each one of the steps requires a lot of attention, a lot of tuning, a lot of, so some actually had to be cancelled because they were lasting for more than a couple of weeks of computation. So this is why you have to understand that here it's 4 different bullet points that represents weeks of work. Yes?
It's called component analysis. So you need the statistical analysis, factor analysis.
For PCA, that's not a statistical analysis. Yes. So we did homomorphism enough, so that's a statistical analysis. PCA is a projection from a higher dimension to a lower dimension space.
Yes, so looking at the model, principal components.
I'm not sure.
And so use dimensionality, the variance in the data.
Yeah. So these are, yeah, statistical, yeah. So, but the vectors, so, sorry, probably my bad. The mean and standard deviation are effectively statistical measures, but the PCA has nothing to do with this. So the idea is to extract from those vectors representing the mean and the variance, to extract lower dimension vectors, the core features that contribute to the space. So
PCA is the outcome.
the PCA is the algorithm. The outcome is a lower dimension vector. So we went from 300 features, so 300 dimension 300 to a dimension of 10. That was a choice we made.
So you found the ones that are strongly correlated together.
Yes. No. No. The one that are the highest contributors to their unicity. So the one that
They create the model when you say highest contributors.
we can discuss that after.
Yeah. You said you would use dimensionality, so the core.
Sorry.
You would use the dimensionality.
Yes.
So if you get the liquid spark components analysis, the ones with gravity dimension. What did you do with base spark component analysis?
Reduce dimensionality. So going from
So what
300
did you end
dimension.
up with?
Sorry.
What did you end up with?
So 10 so with vectors of dimension 10, each one of them being orthogonal to each other.
Yeah, this is factor analysis of problem based. There's statistical analysis. How do you discuss that? How do you do it?
I'm more than happy to discuss that. We carried out, so that was more for the fun, an image analysis. So to try to see if there is any significant difference between fake news and non-fake news. Unfortunately not, but it was still fun to try to see what people were doing in the tweets. So once we have extracted all the disparate features, we wanted to build a model to be able to automatically identify a new tweet using the same features, using the selected features, and tag them if they are fake news or non-fake news. To do so, we tried 5 different algorithms, which are the standard, fairly standard, belonging to different families to make sure that we have a broad scope of results. So as far as I know, there is no prior attempt to this. So for us, it wasn't a matter of improving the performances of the model, but yes.
A couple of CIK papers
Using metadata or using NLP? Because the papers we found were using actually NLP on the tweets themselves, not derived features from the tweet, but NLP itself, to identify linguistic structures and linguistic characteristics to do so. So yes, that there are, but using just metadata, we haven't found them. So I'm sure recently, so a lot of papers so this was submitted a few months ago for publication. I'm sure in the last few months, I don't know how many papers on the topic came out, and I'm sure I'm wrong now that there is no paper on the topic that attempted this. But the thing is, between the time we actually finished that work, submitted for publication, and the others, yeah, it's a few months' time. So, but again, if you want to send them, I'm more than happy to read them. There is always room for improvement. Again, we're not trying to say this is the absolute answer. The results are good, they are not perfect. And I would be keen on seeing others picking up where we left to improve what we have done. And so, as part of the trying to identify which model will perform best, we actually tried different combinations of features, which are described here. So one are just the main features from the Twitter API. Then we added the features from the text. Then we tried sentimentalizers. Then the other type of sentimentalizers, time-related features, and finally we back them all into the same analysis to see how it performed. So without much, it's not very surprising, but the models perform always best with the largest number of features. Interestingly, SVM performed very poorly across the board. That actually surprised us a bit. We hope that SVM actually would fare a bit better than the logistic regression. It wasn't the case. And the gradient boosting methods actually perform best in this. This is only the AUC that I display here, but we actually looked at the AUC and the recall to make sure that we had the more robust model. As I said before, one tricky part was tuning the parameters. So for each model, you don't have just the features. You have, for instance, in the case of random forest, how many trees you use, what the depth, and so on and so forth. You have a lot of hyperparameters to tune. And so we spent an extensive amount of time once we selected the algorithm to tune those parameters to make sure that we have the best model possible. This time we didn't just do the AUC and the recall. We actually tried all the standard machine learning metrics to make sure that across the board we are in a comfortable situation. Finally, so this is the final model we selected using gradient boosting method. We used XGBoost. And as you can see, by far and large, when we put all features into the model, this is always the best model across all the different metrics we looked at. All right. So these results are not perfect, not even remotely. This is what we're trying to establish is a starting base. We collected new data from the Catalan election that we are processing, curating, and putting all through the same pipeline. So this will probably as well give us another idea, another insight on actually our previous data to see where we actually got skewed because of the fact that it's only US elections. So we aim at extracting core features shared across different political news. Again, the NLP go much deeper into text analysis. The problem that we faced is for some of the tweets, we couldn't trace back some of the history of the tweet because we collected them manually. So if we didn't have them in the database, basically we couldn't see where they would go. So we had to discard them. And one interesting idea that we got as well is analyze all the features containing images. So at the moment, we just say, does it have an image? Yes, no. Is it the default image of the profile? Yes, no. A more interesting thing that would be extract features from all the images and see if core features from those images are shared. For instance, the American flag. So we know from the fact from browsing all those Twitter accounts that the American flag on people propagating fake news tend to be there, either in the profile picture or in the background picture. So we want to as well continue to create new features to the model to add them and create new models like this. I would like to thank the team, the Data Science Institute and the Computational Privacy Group that is currently hosting me. Those are the team, with Professor Kugbo being the head of the Data Science Institute. And thank you very much for your attention. If you have any question. All right.
Yeah, so could the people who are publishing news run what they're going to be publishing through your algorithm and choose what they're going to say until it doesn't get classified as fake news?
So yes, Definitely, it's possible. So this is so in science there is something called p-hacking. So you try different combination and different inputs and different parameters until you get the p-value you want. Basically, to be the same, you tweak a comma, you tweak uppercase, lowercase, you tweak. You can engineer, of course, a tweet to be fake news and still go through the filters. Same as spam. Still today, some of them still go through our inboxes. So yeah, definitely it's possible. And we have seen that some, actually what we label as fake news still go through as non-fake news in our algorithm. This is why I say it's never, we are starting on this. There are some literature that starts to come out. And the idea would be someone at the end would pilot all those different techniques. And again, this is political fake news, you have to keep in mind. Maybe for other type of fake news, it won't work at all. So you might need actually n number of models for n number of fake news you are trying to filter. The idea we have is we don't want to be classifying as true or false, because that would be probably wrong. The idea would be to say, okay, how true you are or false you are. That makes a lot more sense to say, okay, there is 80% chances that you're right or wrong. And again, there is temporality. What was true maybe at some point becomes false at a later stage, or vice versa. This is why actually Julio, who is in the list. So Kevin, Miguel, and I carried out all the data science curating, etc. But Julio was the he's part of the business school, but he's a politologist. So for him, it was more the aspect of what the impact of fake news is on society and what filtering them would have impact on society. But he was very insightful to show us that maybe in the same tweet, it would be even more complicated, and that half of it is actual news, and the other half is pure garbage. How do you classify it? Do you filter it? Do you leave it? Do you ask the person to remove one bit or the other? Is it because you don't agree because culturally you don't agree with that, because it's something religious, and you don't agree because your religion doesn't tells you otherwise? I mean, it's very tricky at this point. So we try to take an unbiased level, but another thing we wanted to say is how difficult to actually classify what a fake news is. And it doesn't make sense. So in our case, it's easier to say true or false. But actually, a Bayesian approach with maybe say, okay, this part is likely to be fake, this part is likely to be true. Those are coefficients that say this is 80%. We have 80% certainty this is true. And then actually go through human filtering. Say, okay, this tweet has been flagged. Please, moderator, check if it's within Twitter's privacy and Twitter's correct uses of the platform. Because again, Twitter is not there to say who's right or wrong. It's just prevent people from tearing each other apart through tweets. So again, and there is a lot of filtering. So if you actually, what's interesting is a lot of tweets we had to let them unknown because we were incapable of saying what was shared. So the link that was shared in the tweet, what it was about. Because actually Twitter with time removed them because maybe someone complained, because it was inappropriate, and so on and so forth. So it's very difficult to say. And what we try to say is there are ways to give a likelihood, but a right or wrong is shifting. Yes?
You mentioned at the beginning, when you were training the set of tweets you had, you said there were two labels, and the people who created the second label were more experienced and reliable. What made them more experienced and reliable?
Because when I asked my undergrads some basic questions about American cultures, they would usually don't know. So when I would go over what they would label as, because I label them and I would label as fake news and they wouldn't, I asked them, why do you do so? And then when I showed them that they are wrong, they would usually come around and say, so we left it as is. So we didn't skew the data, we left it, we wanted to be as pure as possible. So, but when I came around and say, why did you tag it like this, and discuss it with them, usually they would come around and say, yes, I was wrong, I didn't know. I use GreyAtom as a reference, and I'm like, you might not want to do that. So please use New York Times or higher quality, please. This is the thing is, some of them have different, so if it's on the internet, for them it's true. Some of them it was a little bit plain. For some of them, they could find a link that says with a journalist that says so, they would usually consider it non-fake news. This is why as well we have a huge, skewedness in their data set here as actually very few fake news. And usually the fake news they identified is someone assaulting and clearly making a joke. Because we had, so what I can show you now is when we actually label them, we label as well what type of fake news we see them as. So is it a joke? Is it trying to distort part of the reality? Is it arguable for X, Y, Z reasons? So we had 5 different categories. So on top of true, so this again, this is just true or false. But we actually, part of the data set we shared, there is a lot more that we did as part of labeling and creation of the data. We filtered a lot of incorrect characters and so on and so on. So we actually cleaned up the data, we created it, we labeled, so true, false, unknown, and int. If it's true, if it's a fake news, then what type is it? Even this is not always agreed. Sometimes what is perceived as a joke is sometimes perceived as actually just someone trying to propagate, to make a false claim. Again, depending, so interestingly, none of the creators were British born or US born or so it's one Australian, and that's it. So all the others were Spanish, French, Chinese, Czech, and the last nationality Australian, as I said, and the last nationality Chinese, I would say. And another nationality I forgot. Anyway, so you see, and from one country to the other, we had sometimes different perception of what is a joke and what is not a joke as well. And the level of understanding of English sometimes made it even more difficult. And when it's Google tried to make things hilarious. So that's actually an open problem. If any of you have a solution for this, I'm all ears because we have been at it for a long time. We have made compromises. That's part of the job. It's same as cooking. Data science as cooking. You need good ingredients, a good chef, but you are not in the ingredients. You cannot always choose whatever will come out of the ingredients. You have to deal with it and make the best out of it. Yes?
So taking the mean and standard deviation of tweets of word embeddings to collapse tweets of a single vector was an interesting choice. Now there's stuff like Doctor-Vec that will do the whole thing out of the box.
Yep.
So were those features particularly effective or more effective than the out-of-the-box approach? And can you speculate as to why they were?
So I will be honest, we didn't try it out of the box. No, so we just don't know. We read the literature. We are researchers, so for us it's always reading the literature, the state of the art, and avoid duplication of work. Again, we started this in 2016. So you can imagine that some things have shifted. Again, we shifted some things with new publications, but this is not the only thing I'm doing at the Data Science Institute. So this is actually a side project we did all together. This is why as well it took maybe a bit longer, but we wanted to do everything ourselves, because one thing I've learned as well is to mistrust libraries. You can argue I'm right, you can argue I'm wrong, My experience makes it very difficult to trust third-party libraries that are not well established. So we do prefer writing our own code ourselves to make sure that it's sound and have a hand on what's going on. So that's a choice we made. We are data scientists. My background is computing and applied mathematics. So I feel confident enough that I don't need to use a toolbox to actually do it properly. So again, the idea is it's two of us, so we always cross-check the work that everyone has done to make sure that we don't miss something. As soon as the paper is out, I'm more than happy to share the code. Yes?
The kind of work you have done, is there a particular reason related politics as a domain? So what I mean is how physical or practical it is to build a solution to get in general, generalized mode.
Sorry, can you use a bit louder? Sorry.
So basically, what I mean to say is, if you try to build a solution, just try to predict any technique, irrespective of what sports, politics.
So we haven't tried because it would be very interesting, and we were interested in doing so. But the problem is the scope becomes enormous. And that's now 2 PhD students and 1 postdoc that could solve that problem. So we try to focus the scope on something we understand and try to solve this one. And as you said, then instead of trying to generalize directly, to try first to see if it works on a small scale. And from this, try to validate, because that's something that a lot of people don't do, is they have something, they think it's a interest, but actually we try to validate with another data set to see if we find the same findings. And once we have this, we might start thinking, what is the ground truth and what is the fake news? Is there already shared commonalities between the two? Yes, no. If they are shared, then that means there is a chance that we can generalize. So at this point, you move to broaden the scope a bit, and then a bit until you can flag any fake news. I'm not sure that's possible. Again, this is for English. Important. This is for English in a Western country. That context is important because the perception, and that's something that when we created, it was really, really clear, is one country to another, what is perceived and the way people present things are different. So you might actually want, for each language, for each country, have different models to represent for that specific context. Is there a commonality between them? Maybe. Yeah.
In the interest of time, can we take maybe one more question?
Yeah, so I actually have 2 quick questions. Why did you not include new sources like variables to explain things versus buildings? And secondly, for your prediction model, in terms of best performing model, was that an outside prediction for forecast accuracy or inside?
It was cross-validated.
So
Cross-validation. We use cross-validation to do this, to make sure. So it's actually what I show is not one run. It's a 5-fold cross-validation for each, to make sure that it's not a sampling issue, which is fairly standard. And the first question was?
Which was, did you include news source as a variable, as an explanatory variable? So news source, did it come from Ocean, did it come from Reuters, did it come from the website?
No, we don't treat the source as, is it Times, is it Donald Trump, is it, no, we didn't consider any of this. Because we don't.
Strong correlation between its probability in fake versus news source.
Maybe, yeah, that's definitely, we didn't do it because that would require extra scrapping of this handle belongs to whom, so you would need to build a dictionary to, is this handle, is this person associated with Reuters, is this person, so that requires a lot more knowledge and a lot more effort than we would actually be able to do this automatically, so we would have to create this manually. Definitely interesting. definitely puts things in context again. What MIT has done is something along those lines. Say, okay, we take to, instead of, so they have tagged tens of thousands or maybe hundreds of thousands of tweets as fake news or non-fake news. So the question is, how did they did so? So what they did is they selected only the tweets that contain specific links to specific articles. And those articles, they would use 6 websites, so 6 verification websites, such as Political, that would then say if it's fake news or non-fake news. They would automatically label this news using those websites. My argument is that's fine. You can work in large scale, and this is how they actually evaluated. When I mentioned this, it's published in Science, and the title is Propagation. I think it's Propagation of Fake News. And then this, sorry, I can't remember. The idea is, the problem is, so, okay, now I'm malicious. I want a specific news, like those websites, to be tagged as true when it's false. So what they did is offload that labeling automatically to third parties. Is it fine? Is it not fine? Imagine 2 of the third parties of the 5 decide suddenly to change the label of a specific article for vested interest. You don't see it because everything is automatic and your filtering doesn't work anymore. Or maybe I'm Reuters, I got bad press, someone is trying to claim something is true when it's to actually give a real news about me, and I want to filter it. So I know Twitter uses MIT's work, they scrap the same website, then I go to this website and say, hey guys, here is a bit of money, can you please change your mind? How do you prevent that? So again, what we want to do as well is not 2 sets of labels, is actually use Amazon Turk to have n number of labels, do an average, to make sure that we have a sort of ground truth using different backgrounds. Again, this is only people from Imperial College, so maybe it's a very skewed population. So you see, there are always other ways to maybe build those models without automatically build them using third parties, etc. Each has pros and cons. This is one method we did. MIT has taken another approach. It's again harder to say who's right, who's wrong, at least in this point in time. I hope I'm not fake news. So yeah, I think the most important is try to show the approach we have taken, the results it gives. Pitfall, so we have almost a page of discussion on the paper to say, okay, this is good, this is bad, this could be improved, and so on and so forth. We have results, as I said, we have what the data tells us with a bit of insight, but definitely there is work to do. Not everything is perfect. There are new methods, there are new techniques to be tried. This is only 5 models. Maybe there are new or different types of models that could be used. I mean, to be continued.
Floor is open for networking. We have access to this particular space for another 45 minutes. So please use it wisely. And once again, thank you so much for spending your time with us.